Okay, hello everyone. Welcome back. I've been quite busy lately, so I wasn't really able to record. I'm sorry about that. It's been quite a while because of it. I was in a vacation and also I bought a new laptop. So I tried to record this lecture for several times, but there was some sort of issue every time. So I had a really hard time recording this. I hope that this is the last attempt. So, if you remember the last lecture, it was kind of an introductory to the PyTorch library, which is a popular deep learning framework that is being extensively used in the industry. So, because of that, I decided to learn this library from the ground up, understanding its core elements. So, hopefully, in the future, I can build advanced models and also workflows, including um, machine learning models and also like data loaders. And maybe, if possible, in the future, I would like to use this library also in my workflow as a ML operations engineer as well. So yeah, in the last lecture, I talked about how to bind your device, CUDA device, and also defining tensors, one of the most important data structures in PyTorch. And also we use different methods to create tensors, including like ones, zeros, or like random generation as well. And we also talked about why they are important. In this lecture, I will be talking about some element-wise operations, some tensor operations, if you want to call it. And also, I will be talking about transposing of a vector, transposing of a tensor. And we will be talking about these, not really much. I will try to keep this short because the last one was quite long. So let's start off with element-wise operations. If you think that the code is quite different, nothing really changed. Still, we import Torch, and there are some additional libraries and settings. Other than that, there's nothing really new here. Let's run everything here and see the results. For convenience, I decided to define the data type as a uppercase data type. So I don't want to write this. I wouldn't need to write this over and over again in the future. So I will just write data type in uppercases. So what are element-wise operations? It's quite self-explanatory, but let's say that I have two tensors. One is A and one is B, okay? The A is M to N in dimensions, and let's say B is the same, okay? These two tensors are in the same shape. So when I am, in case of element-wise operations, it's element-wise. So what that means, every tensor, the shape of tensors are important. In order to successfully execute this operation, the shapes of these two tensors must be the same. So the shapes must be the same, okay? Shapes must match, okay? You can think of these operations as doing multiple operations in between the scalar values in the same location. So if I want to calculate like any element-wise operation between these two, I need to make sure that I am doing the operation in between the elements of these two tensors on the same location. So this is element-wise. Every element is done some operation in the same location. Okay, in the same location. So in our case, the location is important. It needs to be the same location. That's why the shapes must match. So these operations are operations that when you execute it, let's say that you have an input of n, you will get a result of n. You should, you must. Because in order to call this operation element-wise, the output shape needs to be the same as the input shape. Okay, so the result we will get will also be in the shape of m to n. So when you think about these operations, these are adding, subtracting, multiplying, and also dividing. There are others as well. I will be adding them here as well. I'm not going to just write everything here. So let's start off with adding. This is quite, like, these are quite easy. I'm not going to really explain a lot. So adding can be done with a plus sign between these two tensors. Let's first define two tensors with rand method. So we don't really need like a specific result out of it. Let's specify the shape as 5 by 5, two-dimensional. And let's specify its data type as uppercase data type, which corresponds to the torch float 32. And let's specify the device as uppercase device, because that's what I did here. So I'm going to run this, and I'm going to also print some of its attributes as well. So this is our tensor A. It's a 5 by 5 randomly generated tensor, and two-dimensional tensor to be exact. Let's in the same way, let's create another tensor defined as B. Okay, I'm just going to change these into B. So this is our second tensor, again randomly generated. So in order to add these two values into each other, these two tensors with each other, I can use plus sign in between them. So I will get the result. So let's check the result and also its shape, so we can, understand if it's the same or not. So as you can see, this is the resulting tensor, and the shape is the same with the A and B tensors. But what you can do here is you can also use another approach. You can use a global method called add, and you can do the same thing with this as well. So when I run this, I will get the same result again. But let's write the previous one again. So when I hover over this plus sign, this plus sign actually invokes an internal method called add. So in simple terms, doing this method or using the global method are the same. So how can I check this? Let's check this whether it's true or not. So what I'm going to do is I'm going to type in A and B and type in all for all the elements, and I'm going to check if it's equal with torch.add A and B, and let's specify it for the all elements again. So if we are correct, we should get a true value. So when I run this, I get a true value. So which means these two expressions give the same result. Okay. So you can choose to use like this basic syntax, or you can just call the global method. As you know that this also invokes an internal add method. This is probably the same as this one right here. So that's why these both are the same. It's the same for subtracting as well. But in this case, we use minus sign in between the two tensors. You can probably guess, right? It makes sense. When I run this, I will get the subtraction of these two values, and it's again still the same shape. Again, I can use a different approach. Again, there is a global method for this called sub, short for subtracting, and I can specify again the two tensors, and I will still get the same result. Let's check this again if both are the same. Let's add all and also add the other expression, and let's add all again. So technically we should get true again, and we get a true value, which means these two expressions are again same, and they still results in the same value, same tensor. So multiplying and dividing is the same. Let's do the multiplying one. Oh, I'm sorry. I'm adding comments for my own enjoyment. It's not really necessary to add this comment, but I'm just choosing to add it. So in this case, I can use the multiplication operator, you probably know about it already. Let's again print this out. My keyboard is not really that good. Again, I will get the multiplication of two values, and again in the same shape. So let's again use a global method for this. It's called mul, short form multiplication. And again, let's specify A and B for inputs, and let's get the result again. As you can see, it didn't really change. We already know this, but let's check again for this also, so we can be satisfied. Again, I'm going to just add the same two expressions and add all at the end of it, so it will check for all the values. If I don't do this, let's just get rid of these. I'm not, as you can see, what really it does. I will just get the true values for each element separately. You can check with this right here. This is still doable, but I think just getting a single value is much better, because even though if just a single value doesn't really match, we will get a false. So I'm just going to use all for both of them. I'm using for both because if I don't, it's not going to give I think it's going to give an error. Maybe not. Let's check if it's going to give an error. Yeah, it's not. It doesn't really work. So we need to run like this. So lastly, we can do the dividing one. Dividing. And let's again divide two values. I can use a forward slash for this. You probably know about it. Again, let's print it out. Also, its shape. So we can see it didn't change. Again, it's just 5 by 5, and it's the division of in between the two tensors. Let's use another method for this, a global method. It's div, short for dividing. And let's again give our tensors as input, and we'll get a result. Let's again check this if the results add up. Again, I'm going to just use these and adding all, and let's check. Again, this is true. So as I said, fundamentally, these syntax still invoke the internal method that are the exact same thing with the global method. It's just internal, and that's why we are doing it. We can see that for the subtracting as well. Minus sign invokes the sub method, internal sub method, and multiplication invokes probably mul method, and div probably invokes like a div, like true div. Yeah, okay. This also invokes another internal method. So that's it for the element-wise operations. There are some other operations that you might want to do. For example, like exponential operation, exponential, and we can use a global method for this, called exp, short for exponential. We will give an input. We just need an input for this because it's e over a. I mean a over e constant, and we'll get the result of it. And again, if you don't want to do this, you can use the e constant from Torch and use this exponential operator. You probably know about it already, and add an a, and you will still get the same result. Let's check again for this. Let's check if these two results add up. It's quite a work, but I just want to do that because it's a good practice to really check, fact check the operations. I feel like, because we are engineers, we should be able to know if if it works, if it's the same thing. I'm just gonna add a unified parentheses and add all at the end. Oh yeah, this doesn't work probably, yeah. So I need to add all at the end of these. Okay, that's good to know. So it will give out true because it's the same thing. And there's another thing called maybe square root. You can do that too. Maybe you need to calculate square root of a tensor. And I can do that with sqrt, short for square root. Again, I will give an input. It will calculate the square root of it. And you can do this with the exponential operator if you want to be original or different. If you want to do things differently. You can do that with maybe you can do this with this syntax right here, because it's half. If you know algebra, this means that it's square root of a. And let's check if this is the same thing also. I'm kind of curious about it. Let's type in square root again and give input of a. Let's give it add all at the end of it for all the elements, and let's specify the other way. This is a bit weird, to be honest, but I'm just curious. You might want to decide to do this in do the square root operation in this way. I don't know why. So it prints out true, so it's the same thing. These operations are the same. So there's a whole different type of operations that classifies as element-wise. I'm not going to talk about all of them. Element-wise operation simply means that you just calculate the operation in between two elements in the same location. So that's why it's called element-wise, because we are thinking about elements in a specific location. You can think of this as doing a for loop and calculating the result in a scalar values. Okay, this is basically that. So let's talk about so what do I want to talk about? Okay, there's something that I want to talk about called transposing. This is quite important. Before that, I want to talk about something important. I told you that shapes must match in order to calculate the result in case of element-wise operations, right? So what happens if shapes doesn't really match? Okay, what happens if shapes do not match? What happens? Will we get an error, right? So I'm gonna give you an example for this. Let's say that I wanna maybe multiply a vector with a matrix, right? So let's say that I have a vector of v, okay? And let's say that this is n in shapes. So this has n elements, right? This means that it has n elements. It has like n number of elements. And let's say that I have a matrix of M, which has the shape of n to n, right? So this means that this has m rows and n columns, right? Let's also specify that so you can understand everything clearly. So when I want to calculate the multiplication, this should give an error, right? Let's check in code first, and after that I will be calculating the result by hand. In this case, something called broadcasting happens, okay? So I will be talking about that. Broadcasting is simply meaning stretching like a shape in order to match the bigger shape, okay? So what we do here is we stretch a dimension that does not match with the lower dimension alongside the other one so that it matches with the other element, the other tensor. Stretching. I'm probably not explaining this clearly, but I'm trying my best here. Stretching a lower dimension so it matches with the other. So this is the basic idea is stretching a dimension. So this becomes, in order to calculate element-wise operation between these two elements, we need to make sure that this is m to n. So after broadcasting, v becomes m to n in shape. So what happens? So let's see with our own eyes. I'm going to just specify a vector of v and use a range for it. And I'm going to just give maybe start from 0 and end in like 4 and maybe 5 because it's excluded. And is excluded, by the way, if you don't know about this. The interval here is the 5, the end integer is excluded. So this will generate starting from 0 and ending in 4, including the 4, okay? With steps at like 1. Let's do that and let's specify the data type. and device as well. Let's print it out, and also its shape and also its dimensions, because it will change. So the vector, this is the vector that we created. It starts from 0 and ends in 4. The device is CUDA, of course. The size is 5. There is just a single number, and the dimension is 1 because it's a vector, right? So let's specify our matrix with a capital M. Let's you do this by hand. Let's specify our own matrix. I'm gonna create a simple matrix that's easy to calculate the result of. Maybe like, I don't know, like 5. And let's make this into like 3 by 5. It's a great shape. Add in 3, 0, 1, 1, 1, and let's like maybe in the last row add like 10, 3, 2, 1, maybe 4. Okay, and let's add. I'm just gonna add it here. I'm just gonna again add a device also. Let's print it out. Also, its shape and number of dimensions. Yeah, my keyboard is really bad. You can probably hear it. So this is a tensor. This is the matrix that we've created. It's the size 3 to 5, and it's two-dimensional, which means it's a matrix, and we can clearly see that. So we know that these two tensors are not really compatible in terms of shapes. So we cannot, technically, we cannot calculate any element-wise operation in between these two elements. Let's try it, even though it's not going to work, right? Let's use a global method for it, and let's specify with a v, and let's try to print the result out. So that's interesting. You got a result, and it's in the shape of 3 to 5, right? And it's two-dimensional. So as I said earlier, broadcasting happened here because the shapes doesn't match. And as you can see, the resulting shape matches with the element that has the bigger shape, like the bigger dimensions, right? So let's copy these two elements and let's do it by hand so we can understand what happened. I'm just going to first copy the vector to here. Let's type in like example here. Let's specify v as this, and let's add our matrix as well, maybe from here. I'm gonna just copy it from here. This will probably work. I don't know if it's the best thing, but if it's the best way. So this doesn't really match up, so I'm just gonna make sure that this matches with it. Okay, so these are our tensors that we want to calculate the multiplication of. So this has a shape of 5, just a single dimension of, I'm sorry, and this has the shape of 3 to 5. We know that already. When you think this vector as in 2 dimensions, this shape is 1 to 5, right? It's a tensor, it's a matrix that consists of just a single vector, single rows, right? So technically this is in 2 dimensions, is just 1 to 5. Now we can see the second dimension, the columns match. The both elements has 5 columns, technically. So the first dimensions doesn't match. So what we need to do is we need to make turn this 1 into 3, so we can calculate the result, right? So in this case, we make sure that we are not losing any information. So what PyTorch does, it copies the first row and pastes it as the other rows. So now this became, what I'm going to do is I'm just going to copy this after broadcasting. So V becomes V, uppercase V, which means a matrix. And it is, I'm just going to delete this external square brackets. So this becomes now, sorry. This is really hard to navigate. I'm not really doing it practical. That's why. So now this became this new matrix, which has 3 same rows, right? So now this is 3 by 5. So this now the shapes are compatible, and we didn't lose any information. We just copied the same information along the other dimension that needs casting. Okay, so now let's calculate the multiplication, and let's check if the results match with the code. So let's calculate element-wise multiplication. What we're going to do is we are going to multiply 2 elements with each other in the same location. So if I am looking at the first element, like maybe, so this is in the 0th row and 0th column, right? Because it's the first element. We start to count from 0, and I need to multiply this value with this value right here because it's the 0th column and 0th row. Okay, so 0 by 0 is again 0, and I'm going to move on to the second column and first row. So I'm going to look at the same location for the other element. 1 by 1 is going to be 1, and it will be same for the other elements. Okay, 0 by 3 is 0 again. The last element will be 5 by 4 is 20. Let's go move into the next row. 3 by 0 is 0. And that's why I added lots of zeros and ones, because it's going to be easier to calculate. 0 again. 1 by 2 is 2. 1 by 3 is 3. And 1 by 4 is 4. On the last row, we have 10 by 0 is 0. 3 by 1 is 3. 2 by 2 is 4. 1 by 3 is 3. And 4 by 4 is 16. Okay, this is the result we got after considering every rule that I talked about, right? So let's check if these match up. 0, 1, 4, 0, 20, 0, 1, 4, 0, 20, 0, 0, 2, 3, 4, 0, 0, 2, 3, 4, 0, 3, 4, 3, 16, 0, 3, 4, 3, 16. So the results are matching up. So what we did here is correct. So behind this operation, the first thing that happens to the vector is it gets broadcasted into the correct shape. In our case, it stretched the first dimension, which is rows. In order to not lose any information, it copied the existing information and pasted alongside the dimension that does not match up. Okay, so that's what we did here. This is quite important because you need to know what happens to the data you have. If it gets copied, you need to know about it. So that's it for the broadcasting. I hope you understand it. Let's move on to the last thing that I want to talk about. That is called transposing of a tensor. It's quite simple. If I have a tensor of A has the shape of m to n, this means that this has m rows and n columns, right? Transposing means swapping the dimensions with each other. Swapping dimensions with each other. So what this means is rows become columns and columns become rows, right? Let's add it here. Rows become columns, and columns, oh my god, I need to buy a new keyboard. It's quite hard to really type in. Become rows, right? So if I transpose A, I'm going to denote it with dot t, uppercase T. This new tensor becomes and has the shape of n to m. Okay, so let's see it in action. We already have matrix M. I'm going to print it out. Also its shape. This is M, right? So let's get its transpose element. Let's calculate its transpose with a dot t. This is equivalent to calculating its transpose. And let's print it out and also its shape. Okay. So you can clearly see something changed here. When we look at it closely, the shape was 3 to 5, right? It became 5 to 3, as I said it earlier. Rows become columns and columns become rows. In this case, 3 rows became 3 columns, and 5 columns become 5 rows. When we look at it, the first row here is 01305. I'm sorry, 01205. This became the first column, 01205. The second row I have here, 30111, it become the second column, 30111. And it's the same for the last row. Last row became the last column, 103214, 103214. So that's it for the transposing operation. So if I want to do this maybe in a vector, right? Because vector is a one-dimensional data. So let's print out our vector, also its shape. Let's try to calculate its transpose, right? Let's print it out, also its shape. So nothing really changed. This is giving me some sort of future release change. It's depreciated, yeah. Because this is one-dimensional, that's why it's doing it. Yeah, so nothing changed, right? Why? This should change. Because there is no second dimension, we cannot change the dimensions with each other. We cannot swap with this dimension with any dimension because it doesn't exist. In order to do this operation, I need to reshape my tensor, my vector. Again, I need to assign it again. I need to reshape this into 1 to 5. When I do that, I can calculate a transpose of it. Why? Because now we are expressing this as in 2 dimensions. Now this became 2 dimensions. And let's again print this out. So we can see that the dimension is 2. As you can see, the dimension is 2, which indicates that this is now a matrix, technically. But this is a matrix that consists of, let's separate these 2 lines. Okay. So now this has an additional square brackets around it. And the shape will be 1 to 5. And again, let's print its dimensions. And let's see what we'll get. So this is now became a matrix. Now this is a matrix, right? So that's why technically I can calculate the transpose of it, which is what I did. So now this the shape turned from 1 to 5 to 5 to 1. So previously it was 1 rows and 5 columns. Now it is 5 rows and 1 columns. So why did I did this? Like, why is this important? Because this is what we call a row vector. This is a row vector, okay? When I get the transpose of this, this now became a column vector. This is what we call a column vector because its shape is like it just has 1 column. It's a column vector. This is important because you can probably gonna come across the term called like column vector and row vector. So this is what it is. So that's it for today. That's all I want to really talk about. I'm sorry if my English is not perfect. It's not my first language. One of the reasons why I'm doing this is to really not, like, I am not, as I said, I am by no means, I am no professional, okay? I just wanted to learn this library and I just wanted to share it with you guys what I've learned. And with this, I can also practice my English and hopefully improve it also. This is it for today. Thank you for listening. I hope that you learned something new. And I would appreciate if you follow along and comment down the things that you want to see. And I would also like to talk about these, what I talked about. So if you have like a better explanation, I would appreciate that also. And thank you for listening again. See you soon. Take care and goodbye.